Hello and welcome back to Jason Live. My name is Patrick Shea. I'll be your host today as we continue our STEM career series where we learn about careers in science, technology, engineering, and math from role models currently working in those fields. Today's STEM role model is Clara Smart. Clara is an ocean engineer, a member of the Nautilus Corps of Exploration. She's been on many Nautilus expeditions over the past few years, serving as a navigator and contributing her expertise in high-resolution seafloor mapping. She's currently pursuing her PhD at the University of Rhode Island, where she joins us from today. We're going to learn all about Clara and her career in just a moment. But before we do, I want to remind everybody out there that today's event is live and interactive. We want you to send us questions and participate in our polls. To do so, just use the box just below this video window. We'll try to get as many of you involved as possible today. Right now, we want to get Clara involved. Welcome. Thanks for joining us.
Hi. Hello, Jason. World. I'm glad to be here today. This is fun.
It's awesome to have you.
As Patrick mentioned, I am a graduate student at the University of Rhode Island, and I am studying ocean engineering. My background is electrical engineering, so you take that and you pick your sensors that you want to throw in the water, and that's how you get to ocean engineering. And so I go out on the Nautilus, and I've worked as a navigator. I also work as a high-resolution seafloor mapper. So what this means is the ROV Hercules has a couple high-resolution imaging sensors mounted on him. So three main sensors that we use are stereo cameras. So it's a pair of cameras, a color camera and a black and white camera, and as well as a high-resolution multi-beam sonar system, which acoustically maps the seafloor. And then the sensor, which I spend the most time working with, is a structured light laser sensor. So how this works is a sheet laser shines on the seafloor, and where it intersects the seafloor, it almost looks like it's cutting the seafloor. A black and white photo is taken of the laser line at the seafloor, and then from there we can pull those images together. So
Clara, before we move on here, I just want to make sure people understand what we're looking at in that black and white photo. Why don't you talk us through what we're seeing here?
All right, so we use these sensors to map a variety of sites, archaeological sites, biological sites, and geological sites. This is an archaeological site. It's Knidos F, which is in the Aegean Sea near the Dakar Peninsula in Turkey. And what you're looking at is the remains of an ancient shipwreck. Basically, the ship was loaded up with amphora and sank. As the ship fell apart, the amphora just created this large pile. So when we map this site, you'll see an image that, like the one that was just up with the laser line intersecting the seafloor, and it's photographed at the seafloor as well. And then, so these images create a bathymetric profile, so a profile of the seafloor topography, which we can then combine. And when we combine those images, each little laser line, we can get a very, very high-resolution map. This is an example of just a strip, just a little tiny piece of that survey, but you can see the detail, and you can see the handles of the amphora. And just to give you an idea of scale, each handle of the amphora is a couple centimeters wide. Additionally, we have the stereo cameras on the vehicle, which allows us to create beautiful images like this, which is really kind of an eye-in-the-sky view of what the entire site looks like.
So how does your work with the lasers, the laser mapping that you do, how does that differ from ways that we mapped the seafloor in the past? How does that improve upon or give us additional abilities that we didn't have before?
And so high-resolution mapping is really the new pushing boundaries in a new way. With the ability to map things as true to life as they really are, we can document in a way that allows for extreme conservation and a way that we can basically reconstruct the seafloor in 3 dimensions. The laser is the highest resolution imaging sensor that we have. It's capable of being gridded, so every single laser point is equivalent to can be gridded as small as 25 millimeters. So that means anything that is 25 millimeters and bigger on the seafloor will be resolved.
It's pretty impressive.
Yeah.
So I'm sure that the scientists and the archaeologists, the people who are using these maps, they were able to see things they could never see before. They're able to analyze this in a way that they just never had the chance to before.
Definitely. It's the equivalent of having a table that's all set and throwing the tablecloth on top of it and not really knowing what's there versus actually seeing what's there.
Cool. I mentioned before, this is live. We have a lot of questions coming in. We've actually had a number of questions come in even before the event started, and we've had so many of them, I want to get to them as soon as possible. So here is our first question. This one comes from Andrea.
How many jobs have you done underwater?
So how many jobs have I done underwater? Well, if I can interpret that a couple different ways. How many different sites have we surveyed underwater? I actually recently counted the shipwreck sites that we've surveyed since 2009, and that is 65. We have also surveyed a handful of geologic and biologic sites, so probably another 15 or 20 of those sites. And that's just work that my lab has done. I've worked with some of that data. And I've also, when I'm on the ship, I actually have 2 jobs, depending on what I'm out there for. So I navigate and I map. So I do lots of jobs.
And this is you down there in the bottom right-hand corner. You are mapping in this photo in the control van?
Yes.
Very cool.
Sitting at the mapping laptops, telling Hercules where to drive.
All right, we've got our next question coming in here. This one's from Devin.
Do you get any sleep when you're on your trips?
The correct answer is yes. No, it really depends what's going on. There are times when 6 hours of sleep is a luxury. And there are times when things are a little bit more relaxed and you can catch up. It's important, though, to make sure that you have enough sleep, that you're alert and functional, and you can make smart decisions in the moment, because really we only get one chance for this.
So why is it that sleep kind of goes down to the bottom of the priority list when you're out at sea?
Because it's easy to turn around and say, oh, I have to go do that project, and forget the fact that, well, it's been 20 hours and you haven't slept. The other thing is, because we stand 2 4-hour watches a day, so I was usually on watch from 4 a.m. to 8 a.m., and then 4 p.m. to 8 p.m., it kind of just messes up your sleep schedule enough that you have no normalcy. It's not like when you're at home, when you're like, it's 11:30, it's time for bed. So it's a little different.
All right, our next question is coming in from Hannah, and here we go.
What's the hardest job that an ocean engineer does?
Whew, what's the hardest job? Well, my hardest job, as a PhD researcher, there are a lot of days where I just think everything's difficult. But right now, my hardest job is we've worked on some venting detection applications using the laser, and it turns out it works. We just have to make it work really well, which means figuring out every single time it does something silly, why it does that. Mm-hmm. So that can be very difficult.
That's quite the coincidence, because our next question from Zoe and Elena actually has to do with vents. Let's hear what they have to say.
Do you ever get to go down and see the vents in the ocean?
We send Hercules down to see the vents. But yes, we do. Vent communities are a very forward piece of research. It's important to know where these biologic communities are and what they contribute to the ocean. These vents such as this are also thought to be the origin of life on Earth in some theories. So it's important to learn a lot about what's going on down there. What you're seeing in this video is actually an active seep site, an active hydrothermal vent. The flow out of this is very, very diffuse. It's just a couple degrees above ambient. But what you can see your screen, it starts to get blurry. It looks like the image is out of focus, or it looks like it's wiggling. It's a mirage effect caused by changes in temperature and changes in the flow rate, which distorts the image. It bends the light. So that's what the laser picks up. that distortion in the index of refraction is picked up by the laser. And to show you examples of that, that was a big vent in the last shot. It's a very active vent, and as we went over it with the laser, this is what happened. So instead of the laser line being crisp and sharp, like the image of the amphora you saw earlier, it got really, really blurry because the water distorted it, the changes in temperature. And then we can map that, and what we can see then is areas within the vent. So this is the bathymetric profile. So this is a topography of the vent. This shows you where the high points are. But within these high points, you can actually see areas where the venting is coming from. So, next map, yeah. The red dots within this spire, it's the same map. So within this vent structure, those red dots are the sources of the hot venting fluids.
So this is kind of a big deal, particularly for
Really
you, because this is the subject of your research right now for your PhD. Yes. Is that correct?
Yes, it is. It was actually the proof of concept was the subject of my master's thesis, and now making it work and making it really, really useful for science and making it predictable is my PhD.
And why is this important? Why do we need to know where those vents are?
Well, it turns out that detecting diffuse flow is very difficult. When people typically think about deep sea venting, they think of the large mountain-like spires with black smokers or white smokers, and it's really just water that's so hot and combining other chemicals that it appears black or white. Those have been detected, but all the little diffuse flow, so what you saw in that last video where it's really hard to see, that's hard to detect, but it covers a lot more area than those big smoking vents. So it's thought that the chemical and the temperature concentrations in the ocean are more dependent on diffuse flow than they are on the big smokers. Also, we care about the biology.
It's exciting stuff. We're going to get back to our questions now. This next one comes from Jacob.
What are the most important tools that you use?
I would say, so Hercules has those 3 imaging sensors on it, all of which are very important for their own reasons. And the other piece which doesn't get a whole lot of glory on Hercules is the navigation system. So the navigation equipment on Hercules is actually critical for Hercules doing any jobs, for scientists knowing where Hercules is, and for us to make good, clean maps.
So why is that? If you don't know where Hercules is in space, then you don't know how to put your map together.
Exactly.
There you go.
That image that you saw earlier of the amphora pile, that was made up of about 800 photographic images. So if I don't have underlying navigation, putting those 800 images together, it's one of the worst puzzles ever.
And accurate navigation, too. We're going to get back to the questions again. This one's from Jessica.
How many years have you been working as an engineer?
As an engineer, okay, so I started college as an electrical engineer in 2005. So since then, I guess I've been a formal, engineer in training. But I really started working in engineering labs when I was a sophomore in high school. So a lot of years. Actually, 10 years last summer.
And we actually have, if you give me a moment here to switch gears, we have a shot of you in high school working on with milling equipment. What are you making here?
That was at the University of Washington. I was probably a sophomore, or probably a junior, maybe a senior in high school. And I'm not sure what this piece is, but we were building an autonomous go-kart. And so this is a component for that, most likely. Very cool. But there's me 10 years ago. And there's
a few years later, this is an undergrad doing similar work.
Again, building stuff. I'm not sure what I'm working on here, but you got to build stuff if you're going to be an engineer. Cool.
We're going to get back to the questions. One more video question in this segment, and this one is from Sydney.
When you explore the ocean, what do you hope to see and find out?
Well, that depends on the scientific goals of the crews that I'm on. So my job as an engineer is actually really exciting in that I get to work with different scientists who do different projects and who look at different things. So, for example, this summer, I was out on the lake with Dr. Eric Cortez, and he was looking at corals. So that was cool because we expected to find corals, and we wanted to document them. Later on, we were on the lake in Cayman Rise where we were looking for venting, and we were looking to collect biologic samples. So really, I want to find whatever the scientists want to find, and then I want to take good pictures of whatever the scientists want to find.
Makes sense. We're going to go to some text questions now. Our first one is from Emma and Kira Lee in Miss Bound's class. They're in Alaska. They want to know, what is the most interesting thing that you've mapped?
Well, from my point of view, I really like the venting because that's what my research is. So we've mapped some pretty cool vent sites. But this might be a good chance to talk about the whale scours that we mapped. We were off the coast of Cyprus last year, well, 2012, and we kept seeing these gouges in the sea floor. And we didn't really know what they were. They kind of look like the marks that have been speculated to be from beaked whales when they feed or when they do something. People don't actually know. Well, when we sat near them with Hercules, we saw that not only there's one gouge in front of us, but there's one 10 meters in front of us, just outside of Hercules' view. So just kind of on a whim, it was like, well, let's map this area and see what we get. And so as a result, this is the photomosaic. So this is just combining all black and white images. But you can see that not only are there a lot of these gouges, these strike marks, but they're in a pattern. So this was really, really cool because biologists who study beaked whales have never noted this before. They've never noted that there's a pattern, and that image combined with the individual still images from Hercules may allow the biologists to either determine that another creature is making those marks or determine additional behavior for the beaked whales.
Really
so
interesting. Cool. We've got another text question here. This one from Mason and Kikalea. I hope I got that right. Also from Alaska. They want to know, have you actually gone underwater to do your mapping?
Well, fortunately, from my point of view, we humans stay up on board the Nautilus, and Hercules goes down and has all our mapping sensors, and we drive Hercules from the control van, which is on the ship. And so, no, I don't actually go underwater.
All right, we're going to move along here. We've talked a lot about the kind of work that you're currently doing, but we want to get to know a little bit more about your career path. What got you to where you are today? So why don't we start off with a question. This one, another question from Alaska here. How old were you when you started in engineering, and what inspired you?
All right, so I started being interested in engineering in about 7th grade, which I know is really early, but I happened to come across I don't remember if it was a Discover Science type video or an article in National Geographic or something, but it was all about how robotics are used for research and how they're used for research in the sense of like bugs that flew around with little cameras on them, and I just thought that was the coolest thing ever. And so after that, I started working. As you go through high school and middle school, you have to do those projects on, pick a subject. And I started doing some of those reports on robotics and eventually decided that I just wanted to play with robotics and I just wanted to do research with robots. And that led to my electrical engineering degree. And then somewhere in there, I started to realize that robotics occur land, sea, and space. And we know nothing about the ocean in comparison to what we know about land and even really what we know now about space. So I really wanted to learn about the ocean. I also love the water, and that's what sent me down this path.
Well, I think you've just answered the next two questions that came. This one was from Megan. When you were a kid, what was your favorite thing to do in science class?
Build
Anything
stuff.
to add to that?
Build stuff.
And you also anticipated this question from this group of students who wanted to know what inspired you to become an engineer exploring the ocean and not working with robots on land. There you go.
You know, I just thought the ocean was more interesting.
So we're going to jump right to Jaden and Cheyenne, who ask, what do you like best about being an engineer?
All right, I actually really like this question because a lot of people don't really like the answer. If you're going to be a good engineer, you have to be excited about breaking things, figuring out why they're broken, and then fixing them. And if you don't think that's really fun on some level, even if it's really painful in the moment when something doesn't work and you really need it to work, that's what engineering is. And that's why I love it.
So talk to me about the difference between building a thing like from scratch and breaking it and then fixing it. Where do those two things come into play in the process?
All right. So I'm sure most of you guys have learned about the scientific process where you start with a hypothesis and then you develop your tests. And so there's an engineering process. It's kind of similar in that you determine what the problem is and then you present a solution for that problem. And the first part of presenting that solution is like building something, or whether that's coding a program or developing a vacuum cleaner or building a robot. But then you have to test it. So you can't just build something and say, yeah, it's done, go use it, because inevitably it will break. And one of my favorite examples of this was I worked with somebody who did the early credit card swipe machines that you see at like the grocery store. Mm-hmm. They thought it was all done. And then some little kid came and put their whole hand on the keypad and it broke. So you have to figure out where the weak spots are in your design or in your program and break it. Figure out why it broke, fix it, and do it again.
So you always have to include little kids in the testing process because generally they'll break it.
Yeah, and my mom, no.
Cool. Well, we've asked you a lot of questions so far, and now it's our chance to turn it around. You're going to ask our audience some questions. It's time for our polls, and here is our first poll question that Clara came up with. For all of you out there, she wants to know what you think about this. In what grade did Clara decide she wanted to work with robotics? And I think she might have given the answer to this question if you were paying attention. Was it A, in first grade, because it all starts with Legos? Was it B, in 7th grade, because middle school science is awesome? Or was it C, in 12th grade, because you finally have to make some decisions when you graduate from high school? We've got some responses coming in already. 100% so far think it's 7th grade. They might have been listening carefully to that last segment that we just did. We're going to give it a few more seconds here, see if we can convince anybody else to vote for 1st or 12th grade.
I mean, Legos are awesome. I definitely played with Legos for a very, very long time.
We are getting some 12th grade votes here, but only 6%. So, Clara, why don't you tell us what the correct answer is here?
The correct answer was 7th grade. That's when I decided I wanted to work with robotics.
All right, so moving on to poll question number 2. In college, Clara majored in electrical engineering. She just mentioned that. But what was her minor? Was it A, math? Was it B, English literature? Or was it C, psychology? I don't think you've given the answer to this away. Definitely not during the live event. I don't remember seeing this in your career profile questionnaire. So this is kind of a pure guess on our audience's.
Well, I meant to include it in the career profile. If it wasn't there, whoops, no. This is a good question, though.
It is. So far we've got 90% guessing math, 10%, up to 17% think psychology, but math is still way in the lead. That seems to be, a pretty good pairing. Electrical engineering and math seem like they'd go together.
Maybe that was the obvious answer.
It might have been. We've got 11% now think it was English literature, so kind of a mix here, but pretty heavily weighted on the math. What is the correct answer?
The correct answer is actually English literature. I, as an electrical engineering student, was getting tons and tons of math and tons of science and had a couple of electives that I needed to fill. And I needed to just escape from the math and science side of things, and took an English literature class that turned out to be a lot of fun. And I decided I wanted to pursue a minor in that, and I'm really glad I did, because it was only like 7 classes or something, but it really forced me to read and talk about real books, which I love doing, and it just broadens your horizons.
There you go. You got to work out both halves of your brain, right?
You do. You definitely do.
Okay. Our last poll question. What common science fiction and TV investigation show, think like, CSI shows, there's a tool that they use often in these kinds of shows, and it frustrates Clara to no end. Was it A, the super accurate geolocation based on a plant leaf? So a detective picks up a leaf and he knows exactly where this crime occurred because of this one leaf. Is it B, teleportation? I don't know if we see a lot of that in CSI, but definitely in science fiction.
Yeah.
Or is it C, the image enhance button, where you get a blurry image to start with and instantly can resolve that and sharpen it and figure out,
Exactly.
who committed that crime from the grainy video source. So based on the answers here and the fact that Clara provided them, I'm going to guess that all of these in some way, shape, or form frustrate you, but that one of them frustrates you the most.
Right. And
Okay.
my hint to you is, what do I actually do, and why would that bother me?
Well, I don't know if we've pushed that
Well,
to give our folks a chance to respond, but we're going to move ahead. Yeah, my moderator is saying something weird happened. So we're going to move ahead, and Clara, why don't you give us the answer?
so just in case you're wondering, there is no image enhance button in real life. And I work with image data all the time. And occasionally someone will be like, can you just enhance that? No! So don't ask me to enhance anything, please. I will give you the highest resolution available.
So why is it not possible to enhance an image?
So
In
generally,
the way that they do in these shows, at
the
least.
way they do it in these shows, which is why I have a problem with it, is when you take an image of something, you have a fixed number of data pixels and a fixed bit of information within each pixel. So that's finite. You don't have any more information than that. So when you zoom in and you suddenly gain a whole bunch more data pixels, a whole bunch more resolution, where did those come from? You can do tricks to do things
Magic.
like, you can do things to image processing which can trick your eye. But if the data's not there, the data's not there.
It doesn't come out of nowhere.
Right.
But it does help move the plot along a little bit faster.
Oh, yeah.
So we'll forgive them and encourage them to keep on writing science fiction and making those shows. We're going to move along now. We've just got a few minutes left in the program. We want to talk a little bit about your kind of the personal side of things when you're not working, when you're not doing your research. And we have a video question from a student, Carlos, that's going to get us into that segment.
What is your favorite thing to do when you're not working?
So one of the main things I'm doing while I'm not at school, working on research, or on a ship is riding my bike. I do a lot of road cycling, and I used to race when I was in college, and I do a little bit of racing now. But if I'm not here and it's a sunny day, or I just need to get out, I'm probably out on the road on my road bike.
Okay. Here's a question from Rachel, and I love this question, and I hope there's a good answer for it. She wants to know, do you have a nickname that you use either when you're working or when you're not?
Well, my mom has an answer, but no, while I'm on the boat, I actually have acquired a couple nicknames. A couple of the members of the crew, who I'm very good friends with, the ship's crew, I'm not sure where it started, but one of them started calling me Clarita, and that mainly started when they needed something. Clarita, can you help with, Clarita, will you help, do this, or do you have that, or whatever. So now it's kind of evolved that I think the captain calls me Clarita, and quite a bit of the ship's crew calls me Clarita.
That's great. Had we only known at the beginning of this program.
No.
All right, moving on. This question's from Erin. Does your busy life as an ocean engineer affect your at-home life? And if so, how?
Well, that's a little hard for me to answer because this is the life I've always led. But the pieces of it that are different are I don't really have a 9-to-5 job. I have a job that is very, very, very busy, depending on what needs to happen, or a little bit more relaxed if we're waiting for results to come back. It also, the part about me going to sea for a couple weeks at a time to a couple months at a time, I love doing it. It's a lot of fun, but you do have to remember that the real world is going on around you. But yes, I have a fairly normal life, and I have a cat who I take care of, and I have friends, and I have hobbies.
So life goes on, even though we're learning more about the world and building cool things with lasers. Next question is from Sydney. What are some places that you've traveled to in the world? And this can either be for work or for personal.
Actually, first of all, I've traveled all over the United States personally, but for work, a lot of travel that I've done has been with the Nautilus Exploration Program. And my first year on the ship, I went to Turkey and spent time in the Black Sea, and we went to Istanbul and came through the Bosphorus and then the Mediterranean Sea. And then I was in Cyprus the following year. And this last year, I spent time in the Gulf of Mexico, which is really just Texas. And then the Cayman Islands. And then the southern West Indies. So that was really cool.
So really all over. Our
Yep.
next question here is from Jessica. What's the worst problem, I'm going to assume this is engineering problem, that you have run into?
Well, that changes on a daily basis. But but right now, I'm going to go with the fact that all of our computer systems have recently been upgraded. And while in general that's a good thing, it has broken a few things. And so in order for me to be able to create the next set of maps, which I'm supposed to be creating by Sunday, which may not happen, I have to fix that first.
Yikes.
Yeah.
All right, we've got time for one more question. This one's from Brooke. Little off topic here, but interested in your response. She wants to know, or she says, that they build models of underwater homes in her 5th grade science class during their ocean unit. What should a young engineer consider when designing a home under the water?
That's awesome, first of all. Wow, that's really cool. I would totally live in a home that was underwater. I think that'd be fun. Just a couple basic things, though, that we require on land and don't really think twice about. Oxygen. That's not underwater, really. So do you have a way to make oxygen? Also, sunlight. Is that something, are you going to go to the surface and get your vitamin D? Or are you going to have sun lamps? Things like that. The other thing that I think would be really cool about underwater houses would be the ability to garden, like create underwater gardens. So how would you build and develop a strategic underwater garden? And then what tools would you require to harvest and care for that garden?
How about water pressure? Is that something that
I'm
they should
assuming
be keeping in mind? They've got that one covered already. Okay.
I'm assuming.
All right. See, this is why I'm not an ocean engineer. I just go for kind of the obvious things first.
No, I thought that was the obvious one.
Okay. We've actually run out of time. We've had such a wonderful time learning about you and your career. Thank you so much for joining us. We will let you get back to your upgraded computers and give you time to fix your maps, but we really appreciate you taking time out of your busy schedule to be with us today and answer so many questions.
Yeah. Well, thank you. Have a good day.
Our pleasure. All right, before we disappear here, I want to make sure that everybody is aware of next week's event. It's our last Jason Live event before the holiday break, and we'll be connecting with explorer and author Laurie Carnath. Laurie recently served as the 37th president of the famous Explorers Club. She's now focusing her energies on spreading the message of science and education to people around the world. So we're really excited to have her next Thursday, December 19th at 1:30 p.m. Should be very interesting, so don't miss it. Thanks for joining us today. For Jason Learning, I'm Patrick Shea. We'll see you next time. Take care.